So this next factoring approach, again for a very specific form of polynomial, can be a little tricky at first, but once you figure out the one real important aspect to it and practice that technique, then these become actually, I think, quite straightforward, and they always work the same. So we're working with something called trinomials, and specifically this pattern that we've talked about before, the x squared x no x pattern. This is the general form, and we'll come back to that. But real quick, let's just revisit a chapter 5 question. If we saw that question in chapter 5, we know we would draw our arcs from every term of the first polynomial to everything in the second. So we get x times x is x squared, x times 3 is 3x. Then same with the 2. 2 times x is 2x. 2 times 3 is 6. And then we would combine some like terms there in the middle to end up with that as our final answer. X squared plus 5x plus 6. Now the question of chapter 6, being the reverse of multiplication, the question of looking at this and figuring out that it came from here. GCF is not going to cut it, right? The process we learned before, grouping doesn't work because it's not 4 terms. We need a new approach. So to take a quick look at this form, x squared plus bx plus c. Now I'm at b and c, again, general form mean there'll be a number here and a number here. Notice there's no a. There's no number out front of the x squared. This is very important for us. In this class, we're going to only worry about the cases where this x squared has a coefficient of 1, and that's why I'm going to call it the easy case. Basically, I'm going to call it the easy case because there is a different case, but we're not going to see that in this class. You'd see that in the next algebra class. But what's important about this form here, right, this pattern, is if it factors, right? If this thing came from something that was in multiplication form, we know it comes from something of this form, something where we had 2 binomials where there was an x as the first term. Notice, just look back at this problem, the x times the x is x squared. So that x squared would always come from that distribution of that x and that x. Now the question of where would b and c come from is also very useful. We know that these x's determine that x squared. These numbers, these second terms, determine everything else. Because, think about up here, what happened with this 2 and 3? This 2 and 3, the constants. If I go with that very last arc we drew, right, 2 times 3 gave us this 6. This constant term will always come from what you get when you multiply those two numbers together. That's the only place you get that constant term is number times number. But then the b term, right, this value of b on your x, notice that will always come from your 2 middle terms. It comes from this arc and this arc, this 3x and this 2x added together, combined, right? So what's that tell us? That tells us that these two numbers right here, those two numbers, we would need them to do two things. Multiply to c, whatever that value is, but also add to b, whatever that value is. And that should sound familiar from earlier in the semester because that is the thing that I called the number game. We're going to be playing the number game with these two values, and in doing so, really without any extra steps or lines of algebra, we're going to figure out the numbers that fill in those two gaps, and we're going to have our fully factored final answer. So that's the mixed tricks, just kind of reminding you down there, when you have an x squared x no x, where x squared's coefficient is a 1, right, 1 out front, we're just going to use the easy case number game, okay? Down here, just some things I've talked about with the number game. I'll use a factor tree when looking at C. I'll always watch our signs very carefully. And then certainly it's a good thing to remember, you can check all of these answers when you're finished with them. You can check any multiplication problem that we do. Sorry, any factoring problem we do with multiplication. All right, so this first one here, x squared plus 7x plus 10, we see the pattern. But remember, before we do anything, first step, GCF. Now, in this pattern, we can't do a number because this is a 1 out front. We can't do an x because there's no x's out back. So GCF is a 1. Now, at this point, when you recognize this is an x squared x no x easy case, here's what we do. We start with this number over here, the 10. And I think I need numbers that multiply to 10. Well, there's not too many. 1 and 10, and 2 and 5. That's it. Now, specifically, they got to multiply to a positive 10. Okay, so positive means same sign. and I need to also add to a positive 7. Well, the only two that would do that are positive 2 and positive 5. Those will add to 7. So to multiply to 10, but add to 7, it's 2 and 5. And that means we take this thing and we say that it does factor, and it goes into this form where we know the binomials start with x, and they end with those numbers, positive 2 and positive 5. And that's it. That is the entire work. Again, no real algebra steps at all. It is all the number game to find us those two values that complete those binomials. And that's it. Let's look at some more. Next one, x squared minus x plus 6. We see the pattern, but first step, GCF. Again, number-wise, GCF is 1, variable-wise, GCF is 1, so we got that out of the way. Now, x squared x no x with a 1 out front, so it's an easy case. So start with the c, think of things that multiply to c. Again, not many things do. 1 and 6 and 2 and 3. It's a positive 6. So again, these have to be same sign, right? To multiply to a positive. Now they could be both positive or both negative. Now look over here, we want this to add to a negative 1, right? That's what's in front of this x here is a negative 1. So unless you're paying really close attention to signs, you might be tempted to look at the 2 and the 3. But remember, they also have to multiply to a positive 6. So basically, those are your options, or those are your options. Negative 1 and negative 6, or negative 2 and negative 3. One of those four pairs are the only pairs that multiply to a positive 6. And none of those add to a negative 1. None of those work. So we just tried the number game, and none of the pairs worked. That means this thing does not factor. It will not break down using this number game, obviously. And it doesn't break down with the GCF, and grouping doesn't work on it. So when a polynomial does not factor at all, not even a GCF, we call it prime. Just like a number, like the number 5. Doesn't break down to anything other than 1 and 5. We call that number prime. Same idea. We're going to call polynomials prime that do not factor at all. Okay, let's look at the next one. Again, first step, GCF. GCF is a 1, but it's an x squared x no x with a 1 out front. So, number game, things that multiply to 6. 1 and 6 and 2 and 3. Again, got to be a positive 6, so these have to be the same sign, either both positive or both negative. If you want them to add to a negative 5, well, there's no way all positives work, so I'll just throw in the negative signs on them, and then consider, do either of those pairs add to a negative 5, and those do, right? We want to multiply to a positive 6, but add to a negative 5. There they are. So we go to our two binomials that have to start with x's, and then those two numbers fill in those blanks of -2 and -3. And there's our answer. Notice number 4 is almost identical, but it's a positive 5 instead of a negative 5. So first step GCF is still a 1. We want to multiply to a negative 6 now. So that means the numbers are the same, but we need negative 6, so we need opposite signs. So 1 positive and 1 negative must be the case. And so if I want them to multiply to a negative 6, but add to a positive 5 with opposite signs on my numbers, that's got to be it. Negative 1 and positive 6 will add to a 5. And so I can write my binomials that have to start with x, and then a -1 and a +6 to fill them in, and done. And before we go on to the next page, just a reminder that every one of these factoring problems you ever do, you can say, let's check it, by simply drawing your arcs and multiplying it back out. That's all it takes. All right, a couple more on the next page here. All right, so we'll start with GCF. GCF here, notice, is something. 2x squared plus 6x minus 8, they all have a 2 in common. And so I want to point out real quickly that that is very important that we do that and that we find that. Because if we don't, notice we could actually technically not go any further with the problem because this would not be an easy case trinomial, right? This is not a 1. But finding this 2 and factoring it out leaves us with x squared plus 3x minus 4. And now what's left inside is an easy case trinomial. So we won't stop at GCF. If we find GCF, that's great. It just made this simpler, maybe possible to factor, like this one. Now we will work with this polynomial, and we'll do the easy case number game. Things that multiply to negative 4, but then we need them to add to a positive 3. So negative means opposite signs, so it would have to be a negative 1 and a positive 4. So now when I go to the answer, I leave the 2 out front. That's still part of the factored answer. But now we're just breaking this thing apart with the x's out front and the minus 1 and plus 4 for the constants. And that's fully factored. All right, for the next one. First step, GCF. I'll just pretend you said it. So GCF. What do we see? We definitely see some stuff in common. We see a negative out front, which tells us let's make our GCF negative immediately. Then 3, 6, and 9 have a 3 in common. And x cubed, x squared, and x even have an x in common. So negative 3x as a GCF there. All of that in common. Factored out. Now the question of, think of those arcs. Negative 3x times what is negative 3x cubed? Well, all we need is 2 more of those x's, so x squared, positive x squared. Negative 3x times what is negative 6x squared? Well, we would need a positive 2 and 1 more x. And then negative 3x would need to be times a negative 3 only to get us back to a positive 9x. And so again, notice that GCF took us from something that not only didn't have a 1 in front, but it wasn't even an x squared x no x, right? Now with that GCF factored out, now we've got an easy case that we can see if it goes further. Now 1 and 3 are my only numbers that multiply to a 3. To multiply to a negative 3 and add to a positive 2, we're going to need that as a negative 1 and a positive 3. And so we got negative 3x sitting outside here. And then for my binomials that start with x, a minus 1 and a plus 3 to fill that out.